Okay, team. Today we're going to talk about energy and hydraulic grid lines and how to calculate energy loss or head loss in a pipe system, accounting for both major and minor losses. We're also going to use the hydraulic grid line to tell us where in a pipe system, here's a pipe system right here, that the pressure might reduce and go below zero for gauge pressure. So first we will draw the energy grade line and hydraulic grade line for a pipe flow system. We'll use the hydraulic grade line to determine where pressure in a pipe system is negative, and then we'll solve a pipe flow problem looking for major and minor losses. First, a review. The energy grade line is the line representing the total head at any point in a flow system. So that's the pressure head, velocity head, and elevation head. And it's the summation of all those terms in the energy equation. Remember, we looked at the pitot tube where the flow was arrested in front of this little tube. All that kinetic energy, pressure, and elevation was converted just to elevation head above. Now, when we have a manometer where we just have a port going into a pipe, that just records the pressure. That's what the hydraulic grade line is. It's the static pressure at any point in the system. So static means we're not accounting for the velocity head. So it's just the pressure head and elevation. If you look in this diagram, the upper line is the total head or energy grade line. The lower line represents the hydraulic grade line. And water will rise up to the hydraulic grade line if we're just looking at the pressure in the system. So this is just a port measuring the pressure. The velocity head is invisible, quote unquote, here because we're not accounting for the flow of water in the pipe, not using a pitot tube. So that's just calculated based on the velocity. We'll do a siphon demo in class, but I just want to give a diagram here of what this could look like. If we look at the energy grade lines and hydraulic grade line before this siphon starts, we have two reservoirs here. One is lower than the other. And the energy grade line and hydraulic grade line are on top of each other, right? There's all the energy is just represented as the elevation of the surface of the water. Once we start flow in the pipe, that's going to change. So we start flow in the pipe, and all of a sudden we have velocity, right? There's going to be some pressure drop in the hydraulic due to energy loss at this entrance. So if we looked at the minor losses, anytime water enters a pipe, there's some energy loss there. So that's where that sudden drop happens. And that is going to then, we'll have a pressure drop throughout the pipe based off of just the friction losses, right? So we have some friction losses in the pipe. And so overall, we're going to go down. And then that is why the water elevation won't be exactly the same here, right? But what is actually happening when Z, right, the elevation of the water exceeds the total head in the system, right? Can we actually gain energy in the system? We're not adding energy to the system, right? We just got the flow started, but we know that energy is dropping out. If we look at the energy grade line, it's going to parallel the hydraulic grade line just a little bit higher because we do have some velocity in the pipe. So water up here at the top is going to be greater, going to have greater energy because if you look at the total head in the system, at least in terms of Z, than the actual total head. So what's going on? We're not, creating energy here, right? Let's take a look at this a little bit more. Here's a different system. And we're just going to evaluate the different components of head as we move through. So same kind of setup, one reservoir, another. In this case, the pipe goes over a hill to get from one reservoir to the other. So here's our hydraulic grade line in yellow, and it's the summation of Z and our pressure head that gets us up to the hydraulic grade line. And then if we add the velocity head, we get the total energy grade line elevation. So you can see as we travel over to this point, point 2, Z is actually greater than H, right? So the potential energy or the elevation head is greater than the total head. So what has to happen here? We know we have velocity. The velocity heads are going to be the same. So how are we accommodating this? Well, what's happening is that the pressure is reducing. So if you raise your pipe flow above the energy grade line or hydraulic grade line, the pressure has to go down to compensate for the total energy being just H2, right? The energy is still H2 in the system. What happens is the pressure reduces. In fact, if it goes below, it can go below atmospheric pressure. So over here, if we look at the pressure in the pipe, we add Z1, we add the pressure to get up to the hydraulic grade line, and you can see that the pressure head has to be greater than 0. 0 meaning gauge pressure, right, or atmospheric pressure. So it's positive. As we go over here, in order to maintain the total energy at H2, the pressure has to be negative. And so it goes below 0 or below atmospheric pressure. Now for design, this can be very important. Here's an example of a project I worked on when I was at Bureau of Reclamation. It's a water supply project, bringing water from the San Juan River in New Mexico. So here it is coming out of Colorado. San Juan River in New Mexico, and it goes through Shiprock. They're building a pipeline that brings water all the way down to various parts of the Navajo Nation. So a raw water line, and then they'll treat it at different points downstream. So here's the river, the San Juan River. And in order to get this pipeline to the south, there's a profile here. It has to go over a really big ridge. Then it comes back down. You can see this wash right here. And then it starts to go back up. So there's quite a bit of elevation gain here. Just kind of looking in, it looks like to be about 240 feet of elevation rise from here to here across this ridge. So we have real issues when we need to get pipelines over ridges where the pressure has to go way down in order to maintain the total head in the system. Now, why do we care about pressure reducing? Well, if it goes too far, meaning that if the pressure in the system starts to equal the vapor pressure of water, which is actually much, much less than atmospheric pressure, it's pretty tiny. The vapor pressure is the pressure at which water begins to spontaneously boil, right? And when water starts to boil, in this case, we're calling that cavitation. It forms these little bubbles, right? So gas, the water spontaneously turns into gas. Those bubbles implode, and when they implode, they create a little jet that can kind of destroy pipes and pumps and propellers and the like. So we don't like that, and it can eventually degrade your system and corrode it and break it apart. So at 20 degrees Celsius, the vapor pressure of water is equal to about 2,300 pascals. And atmospheric pressure is over 10,000 pascals, right? So it's a really big difference here. And so you have some room for negative gauge pressure, right? It's okay that you might have some negative gauge pressure in a system as long as it doesn't get down to that vapor pressure. We'll recall, so here's the design criteria. It's that the gauge pressure in your system, that pressure head, cannot go below vapor pressure minus atmospheric pressure. So you can have negative gauge pressure, and that's okay, where gauge pressure is 0 at atmospheric pressure, but if it goes below this difference, then you have trouble. So what is that? Well, let's calculate it out. So If we take the difference between vapor pressure and atmospheric pressure and divide it by gamma, 2300 minus 1 times 10 to the 5th, you end up with about 10 meters. So that's a rule of thumb. Our pressure head in a system can't go below negative 10 meters of suction. I'll post these videos of cavitation so you can look at them later. Pretty interesting stuff. Here's an image of an impeller. So this is what's inside of a pump. And you can see pitting in the metal that's caused by cavitation. So this impeller is spinning really quickly. The high velocity head drives the pressure head way down, and you can get cavitation inside of pumps or on propellers. This would be a submarine propeller. And it can degrade the components quite a bit. One other note here is if we did, so this idea of if our gauge pressure goes down to vapor pressure in your pipe, that's at negative 10.1 meters of pressure head. That is, obviously kind of bringing you right up to the edge of cavitation. So a general rule of thumb is to not design a system so that we don't fall below 2/3 of that value. And so that's about 7 meters or negative 7 meters of head. So from a design standpoint, that gives us a little bit of a safety factor. So in fact, we'll say, okay, we can design a system such that the pressure head does not go below negative 7 meters. Now, how do we think about designing a system then? Say we go back to the Navajo Gallop example where we have this huge ridge. We're not going to burrow through this ridge unless we have a really big budget. That's a really big distance there. I think it's a mile across. So tunneling certainly is an option, but maybe cost prohibitive. So what are some other options? Well, we could think about the head loss in the system. So how big is the pipe? What is the head we get to this point, and how much do we lose from friction? We can think about the flow rate, right? So as the flow rate increases, the velocity head increases, the head loss increases, and the pressure reduces. So maybe we can minimize the flow rate in the system or the velocity in the system such that we can maintain the pressure head that we need so that it doesn't fall below. So we've got some design variables we could work with there in terms of the diameter, the flow rate or the velocity, and the head loss in the system that can ultimately allow us to control it and design it in a way that we don't approach that cavitation vapor pressure.